Okay, now we should be good. Okay, welcome everyone to Analytical Physics 3 on a Wednesday in the middle of the semester. All sorts of things going on. There's a cap up this week. It's due tomorrow on Bernoulli, basically all Bernoulli all the time. There is an exam Friday. Oh yeah, that's the other thing, exam Friday. It'll be exam 2. You look confused, Bailey. Exam is Friday. No, well, exam prep should be happening continually, but that's on you. I will be, work same as the first time. There'll be some problem solving. There'll be some conceptual questions. It'll be over the last 2 homework sets. A much smaller amount of material, a much smaller number of equations. Hopefully everyone will get 100 and it will be a happy day. Might be a somewhat shorter test, although the last test wasn't too long, was it? Yeah, so it won't be any longer than the last one. Yeah, any questions on logistics or anything like that? I will post sometime Friday the next problem set that will be due next week. It will be due next Thursday. We've almost already covered everything that's going to be on there, so you should be good to go there. Next Tuesday is Rejuvenation Day. That doesn't affect us at all. We will have class Monday, Wednesday, and Friday, but I assume that labs are canceled next week, so that'll be a nice one. Okay. So we left off in the middle of an example. And the example was, we have a beaker full of water, and we heat both the beaker and the water. Not just how much water is there. We've already solved that problem. That was really easy. More interestingly is, what does the new amount of water read on the new beaker, right? Because it read exactly 1 liter before we heated it. After heating it, what does it read on the new expanded beaker? That's a much harder problem to solve. And there's one that's similar to this, either on the next homework or the one after that. That's kind of conceptually challenging, because our thing that we're measuring the volume, which is the 1 liter mark on the beaker, no longer really measures 1 liter. And we spent the end of last class trying to conceptually think about this expanded beaker and whether the volume inside there will get bigger or smaller. And we came to, at the end of class, I don't know if the realization is not the right word. We came to the consensus, maybe, or at least I came to the consensus that I told you the answer was, that all cavities within objects that are expanding will also expand. Just because you could imagine putting some of that object in that cavity and it would have to expand, and that would not be a problem. So if you have a beaker that is expanding at some rate, the volume inside the beaker will be expanding at exactly the same rate. I did not forget my notes today, so yay. Okay, let me just write that down. Volume inside the glass expands at the same rate as the glass itself. So we can, the volume that was at the 1 liter line inside there is going to have expanded. How much will it have expanded? Well, we know that, or I'm going to tell you that alpha for glass is 4.5 times 10 to the negative 6 per Kelvin. But remember that we really want delta V is equal to Vg times beta glass times delta T. But that's okay, because we know if we have an alpha, we can very easily calculate a beta value. We just have to multiply that number by 3, and we've got the beta value. So this is also VG times 3 alpha G. Volume of the glass, that's not acceleration due to gravity, that's a subscript G for glass, in case you're wondering, times delta, and that's a G. I realize my G's sometimes look like S's. Delta T. Okay, we know all those things. What is the volume of the, what is the volume? Again, we're thinking about the volume inside the glass cylinder. What is the volume inside the glass cylinder? Yeah, kind of. It kind of would be 1 liter, but I want you to get hung up on one thing. It's possible that this glass was bigger than 1 liter. In fact, it's probable that 1 liter was just one marking on the side of the glass. It's probable that the true volume inside the glass is actually larger than 1 liter. We don't really care because we're not solving for the entire volume of the glass. Really, what are we doing? We really want to know what is the equivalent of 1 liter in the new expanded beaker. We want to develop a relationship between liters, which is the volume at the 1 liter mark in the unexpanded glass, and not liters, which is the volume at the 1 liter mark at the expanded glass. I'm going to call those not liters. So really, we just need to know how many not liters there are in a liter. So we don't really, what do we put in for VG? It doesn't have to be the entire volume of the glass. All it has to be is some subset of that we're interested in knowing the ratio of. So I'm going to put in 1 liter, even though it might not be exactly how, in fact, it can't be, or we're going to start spilling water out the side, the true full volume inside the glass. Okay. So I'm going to plug in 1 liter for VG. We know that beta, we have 3 times alpha glass, which is 4.5 times 10 to the negative 6, 1 over kelvins, times delta T. And our delta T, if you remember from last time, was 50 Kelvin, or 50 degrees Celsius, from 20 to 70. Times 50 Kelvin. Great. Multiply all those guys together. Kelvins cancel out, and we're going to get liters, which is nice. You get 6.75 times 10 to the negative 4 liters. Or, if you like, 0.123630675 liters. That's how much bigger, that's delta V, delta volume. That's how much bigger that 1 liter mark now holds. So I could now pour, for instance, 1.000675 liters of a substance and have it fill it to exactly the 1 liter mark on my new beaker. Does that make sense? Because the thing has gotten a little bit bigger. So, what does this mean? The actual volume contained within the 1 liter mark is 1.000675 liters. Or, and we know, we're going to call that a not liter. That's going to be our new unit of volume inside the cylinder. So I can say 1 not liter is equal to 1.000675 liters. And my problem is, what will the new water, expanded water, read on the expanded beaker? Well, all I really need to do is figure out what the volume of my water is in not liters. And that will be what it reads on the new beaker, because the new beaker is reading in not liters instead of liters. So all I need to do now is convert. I already know how much actual volume there is for my water. That's this, 1.02285 liters. I just need to convert that from actual liters to not liters. And then I've got what it will read on my new scale, on my new beaker. So convert V water to not liters. That's my next step. That's easy. I know that V water is 1.0, was it just 10? It was 2285. And I've got a different number here than I had over here. Uh-oh. That's dangerous. This might be, so I wrote down, I didn't actually do this calculation in class. I did it outside of class. And I wrote down this number for this calculation. Somebody do this for me real quick. If you have a calculator open, 4.75 e negative 4 times 1 times, that's just times 50. Maybe I can do this in my head. .75 times 50, or 475 times 50. Somebody got a calculator? 4.57 times 50. It's 2285. Okay, great. Then I have it wrong here in my second time. I got it right last time. That's actually better. This is 2285. Okay, great. Thank you. Okay, so we know that this is 1.2285 actual liters. We need to now convert, but we know how many not liters there are in a liter. All we have to do is unit conversion. I can multiply this by 1 not liter per 1.000675 liters. The liters cancel out, and I will get this in not, it's a straight up unit conversion from liters to not liters. This is going to come out to be, if I've written this right down in my notes, 1.02216 not liters. And that is what should be reading on the new scale on the new expanded beaker. There's going to be a very similar problem to this coming up where you have a steel rod or some sort of metallic rod in an oven, and you're measuring the length of that rod with a ruler. You put both of them in the oven, the ruler gets longer and the rod gets longer. The question is going to be, what is the new reading on the rod on the new ruler? You're going to have to do something similar with not centimeters and do convert. You're going to get, it's going to be easy to figure out how much longer the rod is, but you're going to need to express that in not centimeters instead of centimeters. And so you have to figure out how many centimeters there are in a not centimeter, and you should be able to, should be good to go. Okay. So that can get kind of complicated. Okay, I'm closing the attendance. Thank you for filling that out. Changing topic slightly, although we're still on thermodynamics. We're going to be talking a lot about energy. Of a substance. And this is going to be odd, right? You've talked about energies of objects before, like the energy, the kinetic energy of a spray bottle as I fling it across the room, the potential energy of a spray bottle as I lift it further off the floor. But now we're talking about the energy of a substance, the energy of a table, the energy of a gas, the energy of water contained in a fluid. What do I mean by that? How do we quantify the energy of a substance? I can be talking about a couple of different things. Any thoughts? Sorry? Temperature. Yeah. So what do I mean by temperature? What is it? So you have some sense that if you increase the temperature of an object, the energy of that object or the energy of that substance will go up. And that's an excellent intuition, and it's right. But what is actually changing about the substance when you heat it up?
The kinetic energy of the molecules.
I got a Zoom answer. What did you say? Yeah. So the Zoom answer was the kinetic energy of the substance, and your answer is the energy as the electrons moving faster. Yes, both of those things are right. It really is, temperature really is a measure of the kinetic energy of all the parts, not just the electrons, but all the other particles in the substance as well, moving faster. And so when we talk about kinetic energy, we talk about energy of a substance, again, it's not going to be the substance of all of the kinetic energy of all the particles moving as one. It's going to be the combined kinetic energy of all of the individual very small motions that are happening within the substance itself. As you heat an object up, those vibrations, it depends on what the substance is. If it's a solid, the atoms are trapped there. They can't really move around. So what does it mean to have kinetic energy increase? It means that they're vibrating around at faster rates within the region that they're confined to. And then if they move too fast, they break out of those confines and they actually change from being a solid to something else. Talking about a liquid, again, the mean free path within a liquid is very small. These things aren't moving around before they hit something else, but they are moving faster from particle to particle and collision to collision as you heat an object up. So we're certainly talking about the kinetic energy of the particles. Individual particles. That's true, but there's more. What else? We can also think about the potential energy of objects in our particles in our gas, particles in our liquid, particles in our solid. Yeah, the potential energy. What do we mean by potential energy? I do mean bonds. So I can mean if you've got a water molecule, you've got an oxygen atom and two hydrogen atoms, and you can model the behavior of that molecule very well by a very massive thing and attached to with springs to two very less massive things with springs, right? So you can imagine the potential energy of that spring being an important part of the total energy of that system. Both the kinetic energy of the molecules moving back and forth, but also the potential energy that's on average being generated by these springs and other things as well. Electrons can jump to higher energy levels in atoms. That's a potential energy gained by your substance. And you can imagine other things as well. Potential energy is important as well. There are other things as well. There is chemical potential energy associated with some certain molecules. We'll have an energy just associated with them being bound as molecules. You can talk about nuclear potential energy of the nucleus of an atom, where the energy associated with the binding of the not only the protons and neutrons, but the quarks within the protons and the quarks within the neutrons, giving you some potential. We're going to ignore those particular things, but we are going to be thinking about kinetic energy and potential energy in these bonds as we go along. Thermal energy, but those don't tend to be thermal energy. By thermal energy, so others as well, like chemical and nuclear, those are both potential energies, but thermal energy, when we say thermal energy, we're really just talking about the first two. Okay. Okay, we are not yet going to be interested in, so let's define the energy of a glass of water. you could, I don't know how many atom molecules of water there are, but it's going to be a number that's really big. So there will come a time in your physics career when you're interested in summing the kinetic energies of every single, and there maybe even later in this class, we'll be interested in summing and determining the kinetic energies of individual particles in our gas or in our fluid. Let's not think about that for now. Let's think about total and global changes in energy of our system. And think about delta E. Think now about delta E. Changing the energy of our system and how that's going to happen, and how a change in energy can relate to a change in temperature. So how does that, how does a change in energy of a system happen? So how could a delta E happen? We're actually going to talk about, there's only, turns out, 3 fundamental ways to transfer energy from one substance to another substance. We're going to talk about those in turn, but for now I want to think more generally about not how it's done, but what happens when it happens. So one way is, and this is the way we're going to be thinking about it most in this class, you can simply put a substance in contact with another substance. At a different temperature. I'm going to say or reservoir here. A reservoir is exactly the same as a substance with one important distinction of a different temperature. Energy is transported between them. For example, you take ice cream out of your freezer and you put it on the table. The ice cream is in thermal contact with the air. The ice cream is in thermal contact with the table. Both of those things are at much warmer temperatures than the ice cream. The ice cream thermal energy will on net be transferred from the hotter object to the colder object. The temperature of that colder object should go up. Leave ice cream out, its temperature will go up. You leave hot coffee out, its temperature will go down. We will often be thinking about placing substances in contact with reservoirs. The only difference between 2 substances coming together and a substance coming together with a reservoir is big enough that any energy that you transfer to it or take away from it doesn't change its temperature. It's so much fundamental matter there that it's a drop in the bucket. It does not affect the temperature to draw energy from that substance or put energy into that substance. Like leaving a bowl of ice cream out on the table here is not going to substantially change the temperature of this room. It will substantially change the temperature. We could assume that this room is a reservoir of energy for our ice cream. So reservoirs have energy capacity so large that delta E does not change temperature. Does not have a delta T. Okay. So that is one way. You could put a substance to change a temperature. You could put a substance in contact with another substance of a different temperature, and it will change in temperature. You're adding energy to that system, the temperature should change. There's another way as well, and that is work. So work is another concept from Analyte 1 that we're going to be treating slightly differently in this class than you did in Analyte 1. You might remember from Analyte 1 that one of the definitions of work is the dot product of some force times some distance vector. So the energy of a system, and I'm thinking now of a gaseous system, has some volume enclosed in some container. If I do work on that gas, or let that gas do work by expanding or contracting, that's changing the energy in the gas. That's changing the net amount of energy in the gas. That's a different way, without even being in contact with anything else, to change the net energy in my substance. To either do work on it or let it do work on some plate maybe that's holding it down. Energy of a system can change if its volume increases or decreases. Goes up or down. Okay, now this is where you have to turn off your Analyte 1 brain a little bit. Here's a big warning. There's a convention difference between how we dealt with work in Analyte 1 and how we deal with work in fluids. And it just leads to a negative sign. In mechanics, in Analyte 1, work is defined as the work done on a system. Right? I have a spray bottle here. I have to do some work to lift it up into the air. The force that I'm exerting on this times the distance. It's positive. I'm adding energy to the system by doing work on it. And so the net work is positive, and the energy gained by the thing is positive. It's exactly the opposite for thermodynamics. In thermo, it is the work done by a system that is the important thing. So that same scenario where you have a substance and you let it do work, let's say by raising the plate that is holding it down, that's actually a net decrease in energy for your system, because your substance is doing work, and that work has to come from somewhere. It comes from the energy of the internal system. So it's sort of the backwards. If the work is positive in mechanics, the energy of the thing goes up. If the work is positive in thermodynamics, the energy of the thing actually goes down. So that's a negative sign you have to worry about. So in this case, in the mechanics case, plus W equals increase in energy. Of the system. And in this case, plus W equals a decrease in energy of the system. Okay. So how does delta E relate to delta T? That's the next question. We're going to define Q, define a term, a variable now. Q is going to be so we define two ways that you could change the temperature of an object. I'm going to define Q to be this first one. Adding thermal energy, Q is going to be the amount of thermal energy I've added. If I put it in contact with some other reservoir or something at another temperature, Q will be how much energy I've added that way, specifically. how much thermal energy transferred to or from the system. To positive or from the negative the system. The textbook and most people call this heat. A delta energy, heat is not a physical thing. Heat's a bit of a misnomer, but it's a very useful concept for thinking about this. It is how much energy you have taken into or out of the system by simple thermal contact with something else. Okay, so energy into a substance. I've already talked about that. I'll write it down anyway. Energy into a substance is plus Q. So my Q is going to be positive if I leave my ice cream out on the counter and let it heat up. My Q is going to be negative if I take my hot cup of coffee and set it on the counter and let it cool off. Okay, energy, delta energy, is linearly related to delta T. So I can write this equation down. Q equals C delta T. That's what linearly related means. If I double the Q, I double the delta T. No, that's a capital C, first of all, and it's not the speed of light. It's a proportionality constant. We haven't defined it yet, but it is some proportionality constant that we're actually going to keep calling C, but it's definitely not the speed of light. What is C? It has a name. Anybody know what the name is? It is not the specific heat, although it's very close. It's the heat capacity. It's related to the specific heat. I'm going to get to the specific heat in a minute. But the C, capital C, as we defined it here, is heat capacity. And it is substance dependent. Well, what are the units of C? Joules per Kelvin, it has to be. Q is in joules, delta T is in Kelvin. In order to make this formula work, C has to be joules per Kelvin. Great. Okay, it's easy to get confused because we're writing Q and not delta Q. Q is always a delta. Q is always a change in energy. It is never a total energy of a system. We never will talk about the total heat of a system. You can talk about total kinetic energy of a system, but Q is always how much you have added or subtracted from your system. It is a delta by default. It is a change in energy. It is how much you have added or how much you have subtracted. It is also I'll just write this down. Q, some notes to be aware of. Q is always the transferred energy. Delta E, not the total energy. One other note, C, this heat capacity thing, is extensive property. Meaning, you can't talk about the heat capacity of water. You can't talk about the heat capacity of lead. If you double the amount of water you have doubled the heat capacity of your substance. That's what extensive means. It's a property of a thing, not a material. I can talk about the heat capacity of a potato. I can't talk about the heat capacity of potatoes because every potato will have a slightly different heat capacity depending on how big it is. Property of a thing, not a substance. So it's not all that useful. Heat capacity is not that useful thing. We'd much rather have a property that we could say there is something about water that we could write down that is true for all sizes of water, that is material dependent and not thing dependent. So if for that, so this is almost always the one we're going to use instead. For materials, for substances, Q equals lowercase c times m times delta T. And this lowercase c is also not the speed of light, even though it's exactly this. We just run out of things to call it. And what do we call this little c? That's the specific heat. And it has slightly different units because we have to multiply by the mass of the thing that we're talking about. Specific heat is the same, except it's a per kilogram also. Joules per kilogram Kelvin. So let's write down some specific heats, just so we can have a sense of what this number looks like. Lead has a specific heat of 128 joules per kilogram Kelvin. What does that mean? It means if you have 1 kilogram lump of lead, it takes 128 joules to increase the temperature by 1 Kelvin. That's what that means. Copper, 386. These are all going to be joules per kilogram Kelvin. I'm going to stop writing the unit down. Aluminum, 900. Woo, it's a big one. Glass, on the high end also, 840. And this is a fascinating one. We know what the specific heat of water is? I wouldn't either. Say it again. 4.19. That's right, but it's in a different unit that I'm using right here. That's in kilojoules per kilogram Kelvin. It is in joules per kilogram Kelvin. It's an amazing memory. 4187. 4,187 joules per kilogram Kelvin. That's a huge number. It's more than 4 times more than aluminum. It's more than 10 times more than copper, which is weird. What is it about water? It has major implications for weather patterns and life and everything else. Yeah. So it's the molecules and the bonding of the oxygen and the hydrogen molecules that make. Are you answering the question of why it's so high? Yeah. Did I successfully summarize what you said? Did I miss something? I honestly don't know the answer to this question. Probably it's a chemistry question. In fact, I will warn you, this section it's going to be sounding a lot like chemistry. We're going to talk about moles in a bit. I apologize in advance for the chemistry-ish of this unit, but it's just what we do. Right. Oh, I see. It wouldn't be the bonds between molecules themselves that would be weird. Yeah. Okay. Fair enough. I'm glad you guys know more chemistry than I do. It is weird though. You wouldn't necessarily think naively that water should be so much higher than these metals at preserving heat. It takes a lot more energy to change a kilogram of water 1 Kelvin than it takes to change a kilogram of lead or iron or steel or anything else 1 kilogram of temperature, which is weird. And as you say, it has all sorts of implications for the world. Temperature modifications and near oceans, and weather patterns and life and everything else. Water is weird in several ways, and this is one of them.
Dr. Steinhauer, I have a question.
Yeah, go ahead.
So does this have to do with conductivity as well? Because the metals are more conductive, and that's why like you can dip your hand in liquid nitrogen. I know that like has to do with bubbling and like other things, but like would the specific heat of liquid nitrogen be like really high as well?
So the question is, does this have to do with conductivity? And would the specific heat of something else that has high conductivity also be really high? That's a good question. Certainly, and I'm not sure I know the answer to it. Let me tell you what I do know. How fast thermal heat is transmitted between substances is very related to the electrical conductivity of the thing. I don't know if the heat capacity itself is related to the conductivity at all. And that's a good question. Somebody should look that up and report back next week. Bailey? That's true. Copper has a really high conductivity, probably similar to water, if not higher, and it has a really low heat capacity. Right. It's true. That's a great question. I've already thought about this more in this class than I have ever thought about this before. So your homework for next week is look up a bunch of specific heats of various things, random elements, random molecules, and see if you can see a pattern see if there's something that makes sense as to why some are high and some are low. My guess is that there isn't going to be much of one, that it's going to seem kind of random. But I wait with eager anticipation the results of that thing. Okay, there's another unit to be aware of. Again, as we go through this unit, we're going to be talking about some different things. That's the calorie. Sometimes, again, it's probably chemist's fault that we use calorie. We would never use calories, but sometimes you'll see calories come up. Don't be thrown by that. It's pretty simple. The calorie is defined by the energy needed to raise 1 gram of water by 1 Kelvin. And so 1 calorie equals, you can just write the number down, 4.187 joules. So if you need to convert between a calorie and a joule, you're just multiplying or dividing by 4.187. Not hard, it's just another unit to be aware of. And this is where I'm going to start making my chemistry apologies. It's also sometimes that you'll see, instead of a mass specific heat like we have here, this is the mass specific heat because it's per kilogram. Sometimes you'll see, and by sometimes I mean even on some homework this semester, the molar specific heat. And I'm not talking about your back teeth. I'm talking about, so this will be joules, so have a unit of, I'll say C mole, molar specific heat. We'll have units of joules instead of per kilogram Kelvin, it will be per mole Kelvin, right? 1 mole, M-O-L-E, is just a number, 6.02 times 10 to the 23, Avogadro's number, elementary units of things. i.e. atoms, molecules. It's a weird unit because it doesn't really have units. It's like dozen, right? Dozen is just a number. You can say 5 dozen eggs. And how do you get the total number of eggs? Well, you just have to multiply by 12. Same thing with moles. You want to know if you have 5 moles of a substance, you want to know how much substance that is? You just multiply by Avogadro's number and you get the thing back. It doesn't actually have units. Like dozen doesn't have units, but it's just a multiplicative factor on whatever you're talking about. And it's a really big number, 6.02 times 10 to the 23. Does anybody know Randall Monroe and XKCD? Oh, geez, you should every day, 3 times a week. It comes out Monday, Wednesday, and Friday. Randall Monroe, perhaps the most genius comic writer on the internet today, writes a new comic. They're often astronomy and physics and engineering and science related. He's written several books. One of his books is What If? People will ask him just absurd hypothetical questions, and he will, sometimes absurd, sometimes not, and he will answer them in absurd ways. I might be bringing some of that in. Anyway, it's a great book. One of his questions is, what would happen if you had a mole of moles? Like mole being the shrew rodent thing, right? What would happen if you had a mole of moles? Well, that's a lot of moles, right? So where are you going to put these moles? We'll put them in space, obviously, somewhere. That's enough moles that they form their own, like, they will coalesce into some planetary body with its own atmosphere and things like that. He talks about the physics of decaying meat at high temperature. It gets gross and wonderful and disgusting all at the same time. We'll bring him. Some of his other absurd things come up in this unit too. So, okay, it's not real. So mole, it's not really a unit, but it's also really not a unit. So you have to worry about it being there. Okay, great. So it's also strange because because it's tied to the definition of atomic mass units. Atomic mass units, or just U, is 1.661 times 10 to the negative 27 kilograms. And that's equal to the mass of a carbon-12 nucleus divided by 12. It's also equal to 1 gram divided by 1 mole. So the definition of an atomic mass unit is such that if you had exactly 1 mole of carbon atoms, it would have a mass of exactly 1 gram. So you can take the atomic number up there, carbon's 12.001, that's the average, right? You can take helium, which is about 4, and if you have 5 moles of helium, you can figure out exactly how much that mass that is just by multiplying by its atomic mass unit. So it's related in some weird way to mass, but only because of the way that the atomic mass unit is defined. It doesn't have anything fundamentally to do with mass at all. It just is the way that atomic mass unit is defined. Your mind looks blown, Bailey. What have I done to disturb you? I apologize. It's going to be a little chemistry for the next couple weeks. All right, I'm out of time. We will take this someplace interesting, hopefully physics-y, next week. Friday is the exam. No.